Today's lesson is on finding the area of regular polygons, and first thing we need to know is that the area of a regular polygon is related to the distance from the center of that polygon to a vertex. And you remember a vertex is the point where any two adjacent sides come together. So all these are vertices. Each one is a vertex. Okay, and so what you can see here by this little diagram that I've posted is the center is the center of that circle also, right? So the center of a regular polygon is the center of the circumscribed. Remember that circle is circumscribed about the hexagon, or the hexagon is inscribed in the circle. So we'll say it this way. So the center of that hexagon there in my picture is also the center of that circumscribed circle. And the radius of the polygon is the distance from the center to any one of the vertices, from the center to the vertex. Okay, we have this other thing here, you see, it's called the apothem. The apothem is the perpendicular distance from the center to a side, any side. Go from the center perpendicular to any side, and that is the apothem. And we need to know those things in order to find the area, because theorem 10-6 tells us that the area of any regular polygon is half the product of the apothem and the perimeter. Area is 1/2 AP. Remember that formula. All right, let's do some. So here we have, what is this, a decagon, 10 sides, right? So I'm just going to use my formula I just learned. Area is 1/2 times the apothem times the perimeter. I encourage you to write that formula before you start each of these problems so it will become burned into your memory. All right, so we got a half. The apothem is 12.3 inches. The perimeter, let's see, one side is 8 inches, and since it's regular, all the sides will be 8 inches. So 8, I got 10 sides for a decagon. So all I got to do now is punch that into my calculator, and I'll end up with 492 inches squared. You will have a calculator test in this unit, or at least it'll be partially calculator, because not only do we have some decimals and other things, we'll have to use some trig here in a minute. All right, let's do another example. A honeycomb is made up of regular hexagonal cells. Hexagon, regular, 6 congruent sides and 6 congruent angles. All right, the length of the side of a cell is 3 millimeters. So 3 millimeters. What is the area of the cell? Okay, let's see what we have here. What we're going to do is we're going to try to, we need the apothem, right? We need the apothem. So if I put the center here and I drop the apothem down, there it is. But how do I figure out what that is? Let me draw this radius in here. If I draw that radius in there, I've got myself a little right triangle, right? So I think I'm going to have to use that to help me. So I'm going to come over here, and I'm going to make that right triangle a little bit bigger so I can do some marking in it. So here's our apothem. Now guys, if each of the sides of this hexagon are 3 millimeters long, how long is this little part of the right triangle right here? It's half that, right? So this side length is 3/2. So how am I going to figure out how long the apothem is? Wait a minute. If I look, let's do this. If I come over here back to my large hexagon, I know I've got 6 of those triangles in there, right? See the red triangle? I've got 6 of those. 6 of those, and they would all be congruent if I had a really great diagram. Actually, it's not a bad diagram. But so what I need to do is I need to figure out what the measure of this central angle is, right? So how do I do that? So to get the central angle, I know I've got 6 of them there, so I'm going to just do 360 divided by 6, and of course that's going to give me 60 degrees, right? Each one of those is 60 degrees. But look what I did when I come here and I take this little right triangle, which I've drawn larger over here, I'm halving that 60-degree central angle, right? So that means that angle right there is 30 degrees. Yes? All right, so now I've got a 30, 60, 90 triangle, don't I? That means that has to be 60 degrees. So if my short side is 3/2, then my long side, A is the long side, right? So A has to be 3/2 times the square root of 3. Remember, that's our special right triangle rule. All right, so there we have it. And let's see here. So what am I going to do? If I find the area, look here guys, this is pretty important. If I find the area of this little triangle right here, how many of those do I have in that hexagon? I would have 12 of them, right? So if I find the area of this larger triangle, I've got 6 of those, right? 6 congruent ones. So that's what I'm going to do, is I'm going to find the area of one of those. Well, actually, I don't have to do that. Let me come back to that in a minute. Now that I've got my apothem, I can just use area equals 1/2 the apothem times the perimeter, which is 1/2. My apothem is 3 square root of 3 over 2, and the perimeter is 3 times 6, right? 18. And so what I get when I do that, half of 18 is 9. 9 times 3, so I'll end up with 27 times the square root over 2. And what are our units? Millimeters squared. Remember, area is always going to be square units. But now let me go back to what I was saying about the area of this triangle. So look, let me highlight it again so you know which triangle I'm talking about. This triangle right here, this one that I'm drawing black. Okay, now that I've realized that that's actually an equilateral triangle, right? If this little angle over here is 60, then I know the radii are congruent. So 60, so that makes that 60, and I know my central angle is 60. So I've got an isosceles, I've got an equilateral triangle, right? So whenever you have a regular hexagon, this is a really important thing for you to remember. A regular hexagon that you want to find the area of, all you need to do is find the area of one of your triangles, one of the, like this black one here, of one triangle, and then just multiply it by 6. And this one was pretty easy to just use 1/2 AP, but when we start using trigs to do this, I think you'll find it much easier to remember this interesting little note about a regular hexagon. Okay? So if you want to do it, if you want to go back and work this problem by finding, let's just go ahead and do it while we're here. If I want to use this method right here, then I know what my base is, right? And I know what my height is. So I would say area of the triangle equals 1/2 base times height. Oh heck, I don't need 1/2 base times height. Remember this handy dandy little formula I learned, that the area of an equilateral triangle is the square root of 3 over 4 s squared. But oh shoot, here's s. How do I find out what s is? How do I know it's twice the short side, which is 3/2. So s is going to be 3. So what I got is the square root of 3 over 4 times 3 squared, which gives me 9. 9 times the square root of 3 over 4. So that's the area of one triangle, but I got 6 of those, so I need to multiply that by 6. So let me just multiply that by 6. Let's see, 2 goes into that 2, 2 goes into that 3. So if I do it this way, I still get 27 times the square root of 3 over 2 square millimeters. So please remember that nice little fact about a regular hexagon and finding the area. Now, sometimes we have to use trig. Why do we need to use trig? Because we don't have a special right triangle and we don't know what the apothem is. So let's see how that works. What is the area of a regular nonagon with 10 centimeters. So nonagon, that's 9 sides. You guys have to remember these polygon names because on the quiz or test, I'm not going to tell you what's a nonagon, what's a dodecagon. You got to learn these this time. We got 10 centimeter sides. What is the area? Okay, well, once again, I got to think about the little right triangle that I have down here. I need my apothem and I need my perimeter, right? I don't necessarily need, this is the radius. I don't need to know what that radius is, but I need it because I need the information about this right triangle. Okay, so here's what we're going to do. We can get the perimeter really quick. We know that area is 1/2 AP. All right, the perimeter is 9 times 10, which is 90 centimeters. So the first thing we want to do is we want to find the measure of our central angle. Well, what do we got here? We got a 9-sided polygon, so we know we're going to do 360 divided by 9, right? And that's going to give me 40 degrees. But look at what we're dealing with here. This little right triangle only uses half of that central angle, right? So if let me just come down here. Let me come down here. I like to break out my little triangle. So this is actually this triangle now. So I'm using half of this central angle, so I know this is 20 degrees. Okay, what do I know about this side length right here? Well, it's half of 10, right? This is half of 10, that's 5, so I'm going to label that as 5 right here. Okay, so now here's my apothem. So how am I going to find my apothem? Well, I know that, let's see, what do we got? We got the side opposite 20 and we got the side adjacent 20. So that's going to tell me that the tangent of 20 equals 5 over our apothem, right? Okay, so now if we cross multiply, take the cross product, we'll get a times the tangent of 20 is 5, and then we got to divide both sides by the tangent of 20. So we're going to end up with our apothem being 5 over the tangent of 20. Now, it's very important that you don't punch this into your calculator, 5 divided by 10, 20, and round it off, because then you're going to round off again in the end, and pretty soon we've rounded off too many times. So I'm going to tell you, don't round here. Just leave that as your apothem, 5 over 10, 20, and then we'll just plug that into our calculator in our final step. Okay, so now we need to find the perimeter, which I already did up here. It's 90 centimeters. We're just going to write that in, 90 centimeters. So now to find the area, we know it's 1/2. The apothem, which I got here, 5 divided by 10, 20. And the perimeter is 90. So when I punch all that in and round it off to the nearest hundredth, I get 618.18 centimeters squared. Alrighty. So that's how you have to use trig. And believe me, I have plenty of practice for you, so you'll get a chance to work on this a lot more. You can also find trig to find the area. You can use trig to find the area of a triangle when you know the lengths of 2 of the sides and the measure of the included angle. All you have to do is say it's 1/2 times the length of the 2 sides times the sine of the angle that's included. All right, so here's how that works. What's the area of this triangle? Well, if I didn't know this little formula, it would be very hard for me to figure it out. I'd have to make myself 2 right triangles and use trig and all that stuff. But now we don't have to do that because we have this nice new theorem that says the area of this triangle is 1/2 BC times sine A. If you'll write the formula down a few times, you won't forget it. B and C are the side lengths, so 21 times 12. And then it's the sine of the angle that's included, sine of 48. And when I punch all that in, it didn't say what to round it to, so we'll just round it to the nearest hundredth. I get 93.64 square centimeters. Wonderful formula to remember. Okay, here are your practice problems. I'm going to take a look and see how many I want to do with you. I'll do this stop sign problem here with you, and then after we go through that, you can pause and take a shot at the rest of them. Okay, so we got a stop sign. We know it's a regular octagon. So, you know what? I'm not going to make an attempt at drawing a regular octagon. I'm just going to go ahead and draw my little right triangle like I like to do. Okay, I know this is the apothem. Let me write myself a note. I'm looking at an octagon over here. So that's 8 sides. It's got a 16.2 inch radius. Here's my radius. 16.2. What is the area? Okay, what is the area? Well, what's the first thing we need to do? If you need to look back, you can do so. Number one, we want to find the central angle, measure of the central angle. So that's 360 divided by 8, which is 45 degrees. But we only need half of that, right? Because we're only looking at half of one of the 8 congruent triangles. Half of 45 is 22.5. I typically don't like to use decimals, but it'll be easier to do that here. Okay, so we got 22.5. So now we can just use trig to find our apothem. Oh, we also got to find this too. We don't know what that length is. What do we got this time? We have the hypotenuse, right? Here's the hypotenuse. So we're going to have to use sine and cosine. Hopefully you haven't forgotten your trig. So let's start with the apothem. Let's see, the apothem is the side adjacent. So that's going to be cosine. So the cosine of 22.5 equals side adjacent, which is the apothem, divided by the hypotenuse, which is 16.2. So therefore, we know that our apothem is 16.2 times the cosine of 22.5. Okay, don't punch that in and round it off. We're going to plug the whole thing into our calculator just like this. Okay, now let's find x. Let's find, because we got to have that to get our perimeter, right? So what do we got? We know that's the side opposite. X is the side opposite, so we're going to use sine. The sine of 22.5 equals the side opposite over the hypotenuse. Therefore, x equals 16.2 times the sine of 22.5. Okay, so we know area equals a half AP. We got to get our perimeter. How are we going to get our perimeter? We got to use x. But listen, guys, how many x's are there going to be in my perimeter? This is half of one side, right? So my perimeter is going to be x times 16, right? Because if you think about the regular octagon, it's got 8 congruent triangles, and this side right here is only half of one of the side lengths of the octagon. I hope that makes sense. So our perimeter is 16 of whatever this x value is. So we're just going to plug all this stuff into our calculator right now. Area is 1/2 apothem times perimeter, which is 1/2. Let's go up here, go up right here, and get our apothem. It's 16.2 cosine 22.5. And our perimeter is 16, and by that, this is this 16 right here. That's that 16, and then that's times x, which is right here. So 16 times 16.2 sine of 22.5. I know it looks like a lot, but it's really not that bad. You just can't round it off until the very end. So when I go and punch all that in, I have to approximate it. I'm going to round it to the nearest square inch, and that is going to give me 742 square inches. All right. Okay, if you have any trouble with that, be sure to ask me in class next time, but I want you to pause here and try the rest of these problems. Here we go with your practice problems. This one at the bottom that I've worked in red, you can see it's a regular hexagon, so I just used the triangle trick where I found the area of one of the triangles, multiplied it by 6, and I got 96 times the square root of 3 square units. The next problem, I've got a regular pentagon, and I didn't say these figures are regular, but since that's what we're doing in this lesson is finding the areas of regular polygons, then you just need to assume. I know usually I tell you not to assume things, but you should assume that they're regular if I forget to tell you they're regular. All right, we got a pentagon, so I did the steps where number 1 is I find out what the measure of the central angle is. It's 360 divided by 5 right here, so 72 degrees. And of course in my little triangle I'm only using half that, so the angle that I'm looking at is 36 degrees. I find the side length by using trig, and then I plug it all into my formula. Area is 1/2 apothem times perimeter, and I got about 423.21 square units. In the next one, I'm trying to find the area of the shaded region. So first I got to figure out, well, how do I do that? Well, I've got a large hexagon and then I've got a small one inside of it. So what I need to do to get the shaded region is to find the area of the large hexagon and then subtract out the area of the small hexagon, and then I'll just have what's left there as shaded. So hopefully, and once again, hexagons, love them, because I don't have to worry with the trig because I got the 30, 60, 90 triangle, equilateral triangles, not 30, 60, 90. But so I used my triangle trick, found the area of the large one, area of the small, subtracted, and for my answer I got 162 times the square root of 3 square feet. And finally, for this pentagon problem here, I'm just putting up the answer because I really want you to work this on your own and make sure that you get about that answer that I got there. If you cannot get this answer, then please tell me next time in class and I'll work that out for you. All right, I'll see you next time when we'll be talking about arc lengths and area of sectors.